In this video, we're going to look at linear functions, which are equations that represent a straight line. We usually see linear functions presented in slope-intercept form, which is y equals mx plus b. The b represents the y-intercept, or in other words, the coordinate point is going to have the form 0, b, where b is going to be some real number. The slope is rise over run. In the example on the right, we can identify the y-intercept as being the point 0, 7. This is where the line touches or crosses or intercepts with the y-axis or the vertical axis. For the slope, we want to think about how we are traveling from one point to another. So for example, I'm going to pick kind of an easier identifiable point. So I'm going to look at the point -3, 7. And in this instance, I note that I would have to travel up 2, so I'm going to think of that as a positive 2, and then I'm going to the left 3. And I'm going to think of that as -3 because, again, I'm heading towards lower valued numbers on the horizontal axis. So the slope in this case, which we usually identify with a lowercase m, would be 2 over -3. Of course, we could go in a different direction, so maybe you identified the point as being 3, 3. In that case, I would go down 2, so -2, and then I would go to the right 3, and this would be a positive 3 because, again, I'm heading towards more and more positive numbers on the number line. In this case, we would say that that could be -2 over +3. And what I want you to note here is that I did put an equal sign between these two values. They are equivalent, so the negative can kind of either be with the numerator or it can be with the denominator. And in some cases, what some people prefer to do is they like to put the negative sign in line with the fraction bar. Going a little bit more deeply into slope, we have a formula where it's going to be y2 minus y1 all over x2 minus x1. Those subscripts of 2 and 1 indicate the second coordinate point and the first coordinate point. And what I also want to stress is you get to choose which one you want to be the second coordinate point and which one you want to be the first coordinate point. In this example, let's say I want 2, -6 to be my x2 and my y2. So in other words, my second coordinate point, and 12 and 9 will be my x1 and my y1, or my first coordinate point. So when we set this up, we're going to get -6 minus 9 all over 2 minus 12. Notice the way that I have it color-coded, the second coordinate point values are stacked on top of each other, and likewise the first coordinate point values are stacked on top of each other. We never want to see them located diagonally across from one another. So evaluating this, we'll get -15 over -10, and we always want to reduce our slope if we can. So a negative over a negative would result in a positive result, and 15 over 10 would reduce to 3/2. And just in case you're wondering, well, what happens if I were to have switched the values? What if I picked 2, -6 to be my first coordinate point and 12, 9 to be my second coordinate point? I'm going to show you that it really won't matter. We will still get the same result of 3 over 2. And here we have it at the bottom of the screen. If I switched which one I wanted to be my first and which one I wanted to be my second coordinate point, our setup would now be 9 minus -6 all over 12 minus 2. This would become 9 plus 6 because we have a negative and a negative right next to each other, all over 12 minus 2. This becomes 15 over 10, which once again reduces to 3/2. Now it's your turn. Go ahead and determine the slope between the 2 points, -3, -21, and 5, 11. Once you are done, go ahead and press play, and we'll review the solution. Okay, so for our solution, in this situation, I identified -3, -21 as my first coordinate point, and 5, 11 to be my second coordinate point. My setup becomes 11 minus -21 all over 5 minus -3. Again, when I have a minus and a minus next to each other, we can rewrite that as an addition. So we have 11 plus 21 over 5 plus 3. This becomes 32 over 8, which reduces to 4 over 1, or we could simply write that as 4. If we are graphing a linear function and it is presented to us in slope-intercept form, it's It's actually a pretty straightforward process. The first thing that we should do is identify the y-intercept. In this case, that would be our -8. So the y-intercept would be the point 0, -8, and it would be located right here on our graph. From here, we can identify our slope, or in other words, how we are going to move from that starting point of our y-intercept. In this case, our slope would be 6/5, and we want to look at the signs next to each of those numbers. So a +6 means that we will move up 6, and a +5 means that we will go to the right 5. Again, going back to that general definition of rise over run. So this is going to look like so. So starting at our 8, we are going to go up 6. So we would start maybe around here. There's a tiny little purple dot to kind of indicate where we're traveling, and then we're going to go to the right 5. So our actual coordinate point is going to be at the point 5, -2. Now, you can go ahead and connect those 2 points with a straight line, but if you would like to, you could continue this process. So I might go, once again, from that point, 5, -2, I'm going to go up 6. And then I'm going to go to the right 5. And it just gives me one additional coordinate point, and that might kind of help me maintain a straighter line when I connect these dots. Also notice that when I do connect the coordinate points, they are all aligned with each other. If I had done this incorrectly, you might kind of see that straight line suddenly bend. So that might mean that I didn't count my spacing correctly. Now it's your turn. Go ahead and graph the function y is equal to -2/5 times x plus 7. When you're done, go ahead and press play and we will review the solution. So for our solution, the first thing that I want to note is that I have a y-intercept at 0, 7, and I've indicated that with the green dot on the y-axis. And then our slope is going to be -2/5. So one way that I could read this would be to go down to the right 5. And what I also want to note, just in case this has not been explained to you in previous classes, is you can go in kind of reverse. So in other words, instead of saying down to the right 5, I'm going to change the direction on both of those. So I could go up to the left 5. And you can see the coordinate points for both of those directions. So going down to the right 5 and then going up to the left 5 indicated on the graph for you here. So now we're going to look at a linear function with context, or in other words, with a story behind it. So something to keep in mind, the y-intercept is where we start, or the starting value of something. And the slope is going to be the constant rate at which something is increasing or decreasing. So a general example would be if you've ever worked a job that had an hourly wage. So say you're making $8 an hour. Your slope in that situation would be that $8 because that's the constant rate that you are earning per hour. For the example that we're going to look at, we have the U.S. Bureau of Labor Statistics tracked the cost per pound of dried beans from 1995 to 2021. Assuming the cost per pound changed at a constant rate over the years, we can model this using the linear function y is equal to 5/100 times x plus 67/100. Interpret the meaning of the y-intercept and slope of this function. I'm going to look at the y-intercept first. So our 67/100 or 0.67. And again, in order to correctly describe what's going on, we need to go back and look at the problem and pull context from it. So in this case, we are discussing the cost per pound of dried beans. The other thing that we want to note with regards to y-intercept is that it's our starting point. This is where we started to pay attention. So in this problem, it looks like we started to collect data. In other words, we started to pay attention in 1995. So what we would say for our y-intercept would be the cost per pound of dried beans in 1995 was 67 cents. Now, in case you're kind of wondering, well, obviously people were purchasing and using dried beans well before 1995. That's true, but our model is just starting to look at things in 1995. So this is why our starting point, or our y-intercept, is also going to be tied to that year. For our slope, remember we were talking about how things are either increasing or decreasing at a constant rate. In this case, since our 500ths, or 0.05, is positive, we are seeing an increase. And again, we want to jump back into our story and pull context from it. So in this situation, we would say the following about the slope. The cost per pound of dried beans increased at a rate of 5 cents per year. We can assume that this is annually because of the fact that they are telling us that they collected data from 1995 to 2021. Notice that there's no additional detail in here saying like they collected the data monthly or daily or hourly. So because we don't have any finer details here, we can't make those assumptions that it would be, for example, monthly. So in this situation, we are just going to say, okay, we've seen an increase annually of 5 cents for this product. Let's go ahead and have you all try one on your own. So what I would like you to do is go ahead and pause the video, take some time to read through this problem, and when you are ready, press play and we'll review the solution. Okay, here's our solution. So for our y-intercept, we're going to note that 177 is our y-intercept. So at the start of Craig's weight loss tracking, they weighed 177 pounds. Also, notice this time our slope is negative, so now we're going to see a decrease. Specifically, since we were talking about Craig's weight loss, we're saying Craig has been losing 1.9 pounds per month. Again, note that when you read through the narrative, we are saying that Craig is talking about weight loss on a monthly basis, so not daily or annually. So it is really important to exercise those reading comprehension skills and pull out the details you need in order to give a full and detailed solution.